modeling vibrating systems with damping. Right, so what's the first thing? What's our most important equation here? What's our first equation we want to build? Yeah, our equation of motion, right? So again, we have a system that looks like this, and this is just going to get ugly. Right, that makes sense. Spring damper. It's going to give us a free body diagram of mg pointing down, normal force acting up. Do we care about those? No, they're not special. I mean, everyone's special, but these aren't, I don't know. These aren't special in our context. Okay, so FK, tough crowd. And then FC, right? So we have a force from damping and a force from stiffness. If we go ahead and draw these out, we're going to end up with mx double dot for a function of t is equal to a negative, x is positive to the right, definitely needed, negative FC, that's our force from damping, minus FK, which is our force from stiffness, right? That makes sense? So if I start to move this to the right, Newton's second law gets me my force is equal to mass times acceleration minus my force from my damping, my force from my stiffness. I want a 0 on the right-hand side, and Hooke's law gives us Fk, and then Cx dot gives us Fc. Move them over, we drop our negatives. We end up with an equation of motion, which is mx double dot. I'm just going to drop the t's here, plus Cx dot plus Kx is equal to 0. Right, so if you don't write a lot of things down, that's probably one you want to write down, and that's our equation of motion. Does that make sense? And again, we've got our mass times our acceleration, our damping times our velocity, and our stiffness times our displacement. So now we have 3 terms here. However, we don't have, so once we have our equation of motion, what's the next equation that we've wanted? Or expression? What do we need to make this useful?
A solution.
A solution in what domain? Like what would that solution look like? What would that equation look like? What's on the left-hand side of that equation? Try again. So we want to plot it. Like if you want to plot this in MATLAB, displacement, right? So that's how we've been doing it. I mean, you could solve it for acceleration or velocity, but just solve it for displacement and then take the derivative. That makes sense? So we want to get our x of t equals something. That makes sense? Yeah, so the time domain is what I was referring to that. So we want our x of t, we want our displacement in the time domain. So what we're going to do then is we're going to use our general solution that we used before. So let's walk through that, right? If you remember, if you recall, solve for x of t is equal to something. That's my question mark. Right, going to use our general solution. We had x of t. We assume the solution is equal to a, what did we assume? A e lambda t. Does that ring some bells? Right, remember we just made that assumption. We said we're going to assume that this is our solution. Now we have to fill in the pieces to make that work. Right, so what's x dot of t? Yeah, either a lambda or lambda a. I think we do it like this: lambda a, e lambda t. That how we wrote it, but same thing. I mean, that's what you said. I was just making sure people knew. Okay, and then x dot acceleration. Yeah, acceleration. Take the derivative of that again. X double dot of t. Another lambda comes down. We end up with lambda squared ae lambda t. We went over that a few times. Not a big deal. So our equation, mx double dot plus cx dot plus kx is equal to 0, becomes m lambda squared ae lambda t plus c lambda ae lambda t plus k ae lambda t is equal to 0. That makes sense? Okay, so we have a lot of things here that we don't need, mainly this ae lambda t. So can we divide the entire equation by that? What's the one assumption we have to make? Yeah, it never equals 0, right? So, and we don't say that a never equals 0 or t never. We just say the whole set never equals 0. But sometimes actually when you're coding it up, you may have an error thrown at like t equals 0. You can kind of get in the right spot. So just FYI, when you're coding, you're like, oh, maybe I should just start at 0.0001, and then numerically it works out.
And then lambda e to the t?
No, of course not. Ke lambda t. Right, so let's go and divide that out. We get our characteristic equation. M lambda squared plus c lambda plus k equals 0. So that's a nice simple expression for an equation of motion, right? So now can we solve for lambda? Right, pretty easy, quadratic equation. Let's go ahead and write that out. So, right, use our quadratic equation. We're going to get lambda of 1 comma 2. The 1 comma 2, right, because we have two solutions, is equal to negative c plus or minus, that's what gives us our two solutions, c squared minus 4km over 2m. Right, that's the way we've kind of always seen the quadratic formula. For some of the discussion we're going to have, it's a little easier. You can do it either way, just to break it up. So let's go negative c over 2m plus or minus 1 over 2m times the square root of c squared minus 4km. Okay, so the area under our radical, right, is called our radicand. So this is what we have an interest in, right? So we have c, k, and m, and a negative sign. So can this value become negative? Can you think of a combination of damping, stiffness, and mass where you could make this negative? Yeah, just your damping is less than your damping is more. Sorry, your damping is less than your stiffness and mass proportionally. That makes sense? Yeah, pretty easy, right? You know, if you had a damping of 100, a stiffness of 1, and a mass of 1, all of a sudden if you had a damping of 1 and a big stiffness and a big mass, and then you would have a negative. That makes sense? Okay, but there's also situations where we can have this whole thing be positive. All right, so what we're going to do now is we're going to break this equation up. There's multiple ways to solve this equation, depending on what is in the Radican. Does that make sense? So let's just kind of write that as a note. Depending on what is in or what is, probably what is the Radican. We have 3 different solutions. Right? So we talked about when the radicand is positive, we have a solution. We talked about when it's negative, we have a solution. And what's the other one that you can imagine is important?
0.
Yeah, when it's 0, right? So we're going to have 3 different solutions. So if you kind of draw these out, you can see what your solutions will look like. But let's go ahead and list them. So if c squared minus 4km is less than 0, we're going to say the system is underdamped and solutions are complex conjugate pairs. That makes sense? Okay, so if we take a look at that real quick, if this is less than 0, that gives us a negative, right? Square root of -1 is what?
J.
J, right? Yeah, so it's a complex number. So you have some number here plus some number j, some number here minus some number j. That's a complex conjugate pair. That makes sense. So,
Professor, what does complex conjugate pair correlate to in like physical system? Like, what does complex in a physical system mean? Is that a question?
so in this sense, the complex conjugate pair, it's complex because it's real and imaginary. It's conjugate because it's got a pair that's flipped about the real axis, right? So you have a positive imaginary value and a negative imaginary value. This is just purely mathematical.
Yeah, but I wonder about like the imaginary part of this complex number. What does that correlate?
The way to solve the problem. It doesn't correlate. I mean, it wouldn't directly correlate to anything, not anything in a physical sense. It's storing the information about the problem. That makes kind of sense. Yeah, it's not a direct correlation. Okay, so our next case we want to think about is our transition case. If c squared minus 4km is equal to 0, what do you think the system is? Yeah. And the solutions are equal negative real numbers. And that makes sense. If we look at this, square root of 0 is 0. This whole thing becomes 0, plus or minus 0. Oh, we're just left with 2c over 2m. You know, mass always has to be positive, so we're always going to have a negative value. Make sense? Okay, so, and then our last one is if c squared minus 4km is greater than 0, system is overdamped. And solutions are distinct negative real numbers. Right, so there's 3 solutions for our 2 cases and our special case. 2 cases and a special case. Okay, so from this, right, what's our special value here? What's the one that's kind of important? It's a c squared minus 4km equals 0, right? This is our boundary condition. So let's look at this a little bit more then. So let's call that the critical damping coefficient. So critical damping coefficient. And that's when we have this equals 0. So we call it CCR for critical squared minus 4km is equal to 0. Right? So this gives us CCR squared is equal to 4km, which gives us CCR is equal to 2, the square root of km. Does that make sense? So there's another one that we want to do. Because if you have a square root, a k and an m, what does this look a little bit like? The natural frequency, right? So let's get our critical damping in terms of our natural frequency. But to get that, we have to add a term. Well, we're going to add 1. So this is also equal to 2 square root of m over square root of m square root of km. Does that make sense? Just added a 1 in there. And we can break that out, and that becomes 2m omega n. Pretty cool. So the middle one's not important, but this one, and this one are important. So I'm going to go ahead and box those. Okay, so let's say you're in an engineering meeting, and someone tells you their system has a critical damping of 12. What does that mean? Objectively, do you find, like right now, with what we know, is that number helpful at all? Is it underdamped, overdamped? Do you have any clue? You have a critical damping ratio. You have a critical damping value of 12, right? But it's dependent on this K and this M. So you don't know if it's underdamped or overdamped, just that this CCR is 12, right? Or that's what your system would need to be. So the thought that I'm getting across is we want a more generalized way to explain this, right? So we want to distinguish between different types of damping. So we want a generalized way to distinguish between different types of damping. So we are going to between different types of damping. And we're going to call that zeta. Which, how do I draw zeta? Now I forget. So zeta is drawn like this. Not a decent shot at zeta. Maybe like that. I forget how I do that shorthand now. That is not how we do zeta on the tablet. But Maybe I'll try. Yeah, I shouldn't be lazy. Let's not do shorthand. Okay, so let's use zeta. How does that look? Drawing a few zetas. Does that start to look like something you can get familiarized with? I apologize. It's a hard one to draw and gets a little messy. So feel free to ask if you see it and you're not sure. And this is going to be our critical damping ratio. So zeta is our critical damping ratio. And it's defined as C over CCR, right? So CCR is our critical damping value. Sorry if I missaid that wrong before. That's the value we need for our system to be critically damped. But it doesn't tell us anything about what our system actually is. So C is our damping for the actual system. So the dimensions of this are going to be none, right? It's going to be dimensionless. And this will tell us whether we have an underdamped, an overdamped, or a critically damped system. So if this value is equal to 1, what do we have? Critically damped, right? And if it's greater than 1? Overdamped, yeah. If it's less than 1, underdamped. I think that's right. Right.
This process is just normalizing the damping, putting it as a variable.
Yeah. So it's normalizing the damping and allowing you to have a variable that in an engineering meeting type, both the math and the communication part of it, you could say, I have a critical damping ratio of 1.2. And people will know, oh, that's slightly overdamped, right? Instead of having to give them the CCR, like your critical damping value, and then your actual damping value, and then your mass and your stiffness, and letting them figure it out, right? So critical damping ratio is us to push that all into one index, right? So it's abstract. You don't have any information about your actual system. But if you say, oh, I've got a critical damping value of 0.1, everyone's going to know, oh, that's just not damped at all, right? That makes sense? If you have a critical damping value of 5, that's not moving at all, right? It's going to take like an hour to go anywhere. That makes sense? Just high level, conceptual. So because we have CCR denoted a few ways, we can do this as C over 2 the square root of Km, and also C over 2m omega n. Right? So those are useful. Values as well. It's all the same, just kind of different ways to look at this. So let's go ahead and put zeta there I go again, getting lazy. Okay, let's put zeta into our characteristic equation. So lambda of 1 comma 2, again we have two solutions, is equal to negative zeta omega n plus or minus omega n square root of zeta squared minus 1, right? So we push this back into our characteristic equation, and then I guess we resolve the quadratic. Maybe I should put that note. Right? So we resolve our quadratic equation, and we end up with this expression here for lambda. And again, all we're trying to do is to get to a t of x value. right? So this solution does tell us a few things, though. But the most important thing that we want to know is what are our zeta values. I guess we said them, but we didn't write them down. So let's go ahead and write those down. So we have an underdamped. You know what? Let's just go back in our notes. Let's just add it here. So let's just add it here. So zeta. So for an underdamped system, zeta is going to be greater than 0, but less than 1. That make sense? And then for a critically damped system, what's the zeta going to be? 1 value? Yeah. And then for an overdamped system, zeta is going to be greater than 1. That makes sense? So you can now see kind of how your zeta, your c squared minus 4km, and then your solution's complex conjugate equal negative or distinct negative numbers kind of all feed together. So that kind of sets up our problem of we want x of t, right? But the quadratic formula here really throws us for a loop. We're going to have 3 distinct solutions. So we're going to have to walk through each one of those solutions one at a time. Yeah, go ahead. I did something wrong there. You are correct. Let me just do it like this. 1 less. Thank you. Is that better? Thanks.